Good morning, all. Welcome. Just going to wait for a few more people to arrive. Okay, so welcome to another spring showcase. Today we're going to be learning more about the alternative methods to phosphorus removal at wastewater treatment plants that are being explored by United Utilities as part of the OFWAT Water Breakthrough Challenge. My name is Leah Bodley and I'm a Marketing and Communications Executive here at Spring Innovation. For those of you who don't already know, we are the Innovation Centre of Excellence for the water sector, supported by all the water companies across the UK and Ireland, as well as the supply chain and academia. Our goal is to enable collaboration, remove duplication and accelerate innovation within the water sector. Spring are the custodians of the Water Innovation Strategy 2050. So for anyone who hasn't seen that document, we will share a link to that in the chat. It lives on our website and it outlines 7 main themes with challenges sitting under those themes that we are currently trying to tackle in the sector. Spring also puts out calls for innovation against those themes through our Accelerator service. You can find out more about the current Spring Accelerator 3 programme on our website, and I also recommend joining our mailing list so that you are the first to hear about our upcoming accelerators coming out around September. But today's service offering is all about knowledge sharing. We have 2 aspects to that. The first being our knowledge library on our Spring platform, where there is a bank of over 60 case studies on innovation projects from across the sector for you to go and learn from. Recordings of our previous showcase events, as well as any supporting links and documentation, also sit alongside these case studies. Today's showcase will be uploaded onto the same platform, so I recommend you follow the link and create a membership if you haven't already. With another 200 more case studies currently in the pipeline, our platform is constantly being updated. So I do really encourage you to follow that link and create a membership, which will be in the chat in a moment. I'd just like to give a warm welcome to our international audience today. Thank you so much for joining us, and we hope you find the session valuable. Today, you can expect to gain a holistic view of the cost, capability, operation, maintenance and carbon impact of various phosphorus removal approaches, namely electrocoagulation, natural coagulants and reactive media. So these showcases are all about being able to learn a little bit more about the project and take away those learnings and the knowledge, being able to embed them in your organisation. With over 3,600 people registered for these events so far, we are really proud of how these events are helping to disseminate the vital knowledge surrounding water-based innovation projects and accelerate learning across the sector. That being said, we will be launching a poll at the end of the showcase to find out how interesting you found the information today and how likely you are to go away and embed that in your own organisation afterwards. So please do submit your answers at the end of this event when that poll does come through. You'll also get the chance to ask the project team any questions throughout today's showcase, which will be addressed during the Q&A at the end of today's session. So make sure to keep putting any queries in the chat throughout today's presentation. So on to today's session. I'm just going to quickly run through the agenda and introduce our speakers before I hand over to the team. So we have the introduction to United Utilities as a company and the OFWAT competition as a whole. Then we go into a little bit around the importance of knowledge sharing. Then we'll hear from Lisa on work packages 1, which is all about electrocoagulation, and work package 2 about natural coagulants. Then we'll have a quick 15-minute break, and then we'll come back to hear about work package 3, which is all about reactive media. And then we'll have a project wrap up and hear some lessons learned from the project as well from the team before they're going into our Q&A session. So today's speakers, we have Lisa Mansell, who is Chief Engineer of Innovation and Carbon at United Utilities. We have Callum Grundy, Senior Process Engineer at United Utilities, and John Williams, Professor of Environmental Technology at the University of Portsmouth. So thank you so much to all our speakers today. And yeah, with that being said, I'll hand over to you, Lisa.
Thanks, Leah. Hopefully you can hear us okay.
Yes.
Great, thank you. So yeah, Leah just said I'm Lisa Mansell, Chief Engineer for Innovation and Carbon at United Utilities. We are an engineering innovation function that works really closely with our central innovation team looking after lots of innovation work at United Utilities, lots of different types of projects, short-term, longer-term innovation projects, and some of the projects that we work on are the OFWAT innovation competition projects, and one of those we're going to talk to you about today. The project is Alternative Approaches to Phosphorus Removal at Rural Wastewater Treatment Works. And it's really fantastic to be here as the lead water company, United Utilities, representing our collaboration of a number of water companies, electrocoagulation suppliers and academia on this project. And we'll talk to you about who those project partners are in a moment. And thanks very much to Spring as well for letting us showcase this project on the Spring platform today. So, as I said, this project is a collaboration. United Utilities are the lead partner, and just recognising that we've got quite a number of different people from across the globe on the session today. We just wanted to let you know a little bit about United Utilities. We are a large company. We're a water and wastewater provider. But that's not all we do. We do a lot of other work in our catchments. We have 57,000 hectares of catchments to look after. We're a big employer for the Northwest. So there's so much more that we do at UU than just water and wastewater. We work in a very changing regulatory sector, and part of what we're going to talk to you about today is how we're recognising the changes in regulation and trying to be on top of those and be ready with our innovations to be able to adopt those at pace and to maximise the value that innovation can bring in a changing regulatory sector. And we are a company that focuses on innovation. It's a real significant part of what we do and what my team do and the Central Innovation team do at UU. We have an open innovation model. We engage people in innovation, and we love to adopt new ideas that our people bring either internally or throughout our partners and supply chain. And as we kind of talk about supply chain, we love to encourage ideas from our suppliers. We adopt those, we test them, we work with our supply chain to really try and make those ready for use at UU and at other water companies in the way that we're showcasing today with this OFWAT innovation project. And yes, as I said, we like to accelerate ideas to adoption, and this ALT-P, as we like to call it for short, project is really showing how we can recognise good ideas, move quickly on testing and proving them, and take them at pace into adoption, ready for use on our capital programme. And we're really focusing more on sharing our story, really kind of sharing our knowledge, and again, that's why we're here today. We have lots of different methods in terms of how we use methods to test and understand new innovations, and to really take that strategic approach to the things that we should be working on. And part of that is working on the OFWAT innovation competition and using that sector strategy, the 2050 water sector strategy, to really hone in on the types of things that we should be looking at and pushing them through different means of funding, with the OFWAT innovation competition being just one of those in terms of leveraging funding through that competition. And I think the next slide should talk to you a little bit about the OFWAT innovation competition itself. So it's a £200 million innovation fund to help the England and Wales water sector grow its capacity to innovate and really kind of meet the evolving needs of our customers, society and the environment. And the fund aims to go beyond the sector's business as usual innovation practices and create significant value for customers, society and the environment. And in AMP7, that fund was £200 million. That will run to 2025. So we're nearly at the end of our investment period in England and Wales. We run in 5-year cycles. And in AMP8, we're looking at an increased innovation fund and more competition. So we're really excited to be stepping into that into AMP8. And there's a couple of links on the screen there for places you can go to find out more about the OFWAT innovation competition. There's actually 3 components to the competition. There's the OFWAT Discovery Challenge, which is led by suppliers, but the two that are led by water companies are the Water Breakthrough Challenge Transform and Catalyst programme. And we sat within the Transform stream for this project. There's just a couple of things I wanted to talk about in terms of OFWAT Innovation Competition as a bit of understanding for people that maybe haven't been so active in the competition before, or this is new to you. They're collaborative in nature, so the projects were expected to actively collaborate with supply chain partners, academics or other water companies on these projects, and projects by an individual will not be accepted. The project results must be shared and be available and to use by the rest of the sector, and that's why we're here today sharing some of our learning so far before we've reached the end of the project. And OFWAT require a 10% financial contribution from the consortium that's bidding. I'm really happy to share that we've been able to secure that in our bid, and I'll talk to you a little bit more about the value of the project. But this 10% has to come from the supply chain partner or academic institute or another funding body. Or the other alternative is that it comes from the water company itself, but it must come from profits and it cannot come from customer money. So we've been able to secure that on this project, and we'll talk to you a bit about who's worked with us on securing that 10% so that we were able to access the OFWAT Innovation Competition funding, which we're very thankful for. Just to go back a little bit to our open innovation model and talk to you about why that brings mutual benefits, and to cover a bit about why we would like to knowledge share and why knowledge sharing is important. We think that our open innovation model brings diversity of thought, it brings curiosity of mind and a real doability, so really kind of working on challenges together and bringing mutual benefits to ourselves as water companies, but to our supply chain partners, to academia and all the other partners that we work with. And to do that, we work really hard on a few key things, so finding and persuading people to bring their ideas forward and for us to get that ability to fund these projects. We look at brokering and testing, and Callum's going to talk to you quite a bit today around the testing that we've done on these technologies within the OLP project. We focus on adopting and optimizing, and that's a real key focus of my team in engineering innovation, is how do we transfer these learnings from innovation projects into our capital programme or into our business areas, really driving the benefits of the innovation that we're looking at. And finally, sharing and endorsing. So this is the knowledge sharing aspect to this. We really need to share knowledge for a couple of reasons, and I'll talk about those now. So we need to share knowledge because this accelerates innovation. So working together with others, we can really drive better ideas. We can form our ideas that are relevant to all parties, that really kind of focus on the success of each person within the partnership and beyond, so that we're sharing those with the sector so that others can learn and benefit from the work that we're doing. We knowledge share to improve efficiency, so we want to make sure, as Leah said before, we're not repeating these projects, and part of the OFWAT innovation competition was really around trying to make sure that water companies are working together on innovations and not repeating trials. And that's really important for our supply chain as well, because that can be quite a burden on them if we're repeating the same trial at every water company across England and Wales. We need to focus on fostering collaboration. Sorry, knowledge sharing enables us to foster collaboration. So sharing and improving our ideas is really valuable. And we've really seen within the OLP project how combining ideas together can really actually drive further benefit, and Callum will talk to you about that today. And we can enhance problem solving. So as we know, working together with that diversity of thought really helps us to focus on problems and how we can solve them. So we're really here today to share that knowledge on what we've done within this project, but in the whole context of the water industry, improving how we share knowledge in England and Wales. So as I mentioned, our project is alternative approaches to phosphorus removal at rural wastewater treatment works. It's a OFWAT innovation funded project, just as a reminder for that, but I know I've talked about that a little bit already. And it's a combination of the partnership that you'll see across the bottom of your screen between two other water company partners, Southern Water and Wessex Water, and United Utilities, obviously, as the lead partner on the bid and the delivery of the project. We also have John on the session today from University of Portsmouth, and University of Portsmouth have been a real support to us in delivering one of the work packages that John's going to talk to you about today. And then really excitingly, we were able to secure 4 of the electrocoagulation suppliers as partners on our project. So these guys really impressively were supportive of putting their technologies side by side on a test against our conventional way of removing phosphorus. And they were that keen to get involved that they became partners on the bid, and they put up some funding to help us with that 10%. So we really thank everyone that is part of our partnership for doing that for us and making this project the success that it's been so far. So phosphorus removal at rural wastewater treatment works. Why do we need these alternative approaches? Well, our conventional way of removing phosphorus is really reliant on metal-based coagulants. It is pervasive across the whole of England and Wales, and I know many other countries across the globe is really focused on removing phosphorus requires chemicals. And for us, as a water company in the Northwest, we've got some really challenging drivers to deliver in very small rural communities. We've had that in our current investment period in AMP7, and we can just see lots more of that in AMP8. And that was the same across a number of the project partners that were interested in the project, and specifically for Southern Water and Wessex Water. This is a real challenge for us, and why we put the project together. So we needed to look at alternative approaches to improve the quality of water in our rivers. So we've got a number of phosphorus removal drivers in AMP7, around 900 of them, and we're seeing a similar magnitude as we head into our next investment period. And as I said, these will mostly be delivered with chemical coagulants, and this has an impact on our carbon footprint. Chemical coagulation has a significant carbon impact. And for some water companies, there's also the associated alkalinity correction. So the chemical coagulant is acidic, and we need to correct alkalinity. And the caustic that we often use for that is also really significant on our carbon impact. And we need to reduce our impact on rural communities. So we're very conscious that in rural areas where we need to remove phosphorus, the impact of chemical dosing in these areas means lots more tankers on the road for chemical deliveries. And we want to minimise that impact. We want to be a good neighbour, and we've really been looking for different ways that we can remove phosphorus without chemicals and without those tanker deliveries at these sites. And finally, to produce greater operational resilience. So we have been impacted during COVID and other times by security of supply of these chemical coagulants, and really around the quality as well as the quantity that we're able to get hold of in those times becomes a real significant risk to the environment in terms of our environmental compliance if we are reliant on chemical coagulants for removal of phosphorus. So it's really important for us to move away from that, and to also consider the impact of dosing metals for phosphorus removal. As we're removing one thing to replace, sorry, we're just running out of battery, so we're just going to plug back in. Is removing phosphorus with a metal-based coagulant is you're adding metal into the effluent that you need to manage in terms of managing your iron compliance, and so it's not to impact watercourse, but also a lot of that iron ends up in the sludge, and we really need to think about that in terms of security of the land bank for us in England and Wales, where we recycle a lot of our sludges onto land. So just looking into AMP8, so we know that phosphorus targets are getting much more pervasive across all of our sites, as well as the kind of level of that phosphorus limit is driving down lower and lower as we've moved through the AMPs. And we have lots of ways that we've been trying to tackle this in terms of that standard chemical dosing approach, both at UU and across the water sector, in things like biological phosphorus removal, but that is much more applicable to large wastewater treatment facilities and less so to small rural sites. And at UU, we had been looking at adsorptive medias or reactive medias, and we've been working with lots of other water companies for a number of years on trying to share that knowledge. So we thought that maybe the place to take that was into the OFWAT competition. We also looked at electrocoagulation, and we were really excited about this as an alternative method. So Callum will talk a little bit more about what this means, but for us, we didn't have certainty on the operational and maintenance costs of these things, and we were unable to convince our supply chain to work with us on these projects where we would ask them to guarantee the operational costs from these technologies. And then finally, we'd worked with Isle Utilities on an alternative to chemicals, so chemical-free treatment project with a number of other water companies, which highlighted some really interesting bio-based coagulants that could be used. So we thought that we would bring those as a sector level and prove those within this project and be able to share that across the sector for something very new and novel, which again Callum will talk to you about in a moment. So our proposal was a collaborative partnership to address this significant problem for the water industry. It was a £3 million innovation project that we put forward. And as I said, we had a number of water company partners as well as the electrocoagulation suppliers working with us. And then we have some other names on the slide there that you'll see. So we've been working with Jacobs and Stantec to support the project, as well as one of our construction partners, C2V Plus. We've had some advisory members of other water companies, Yorkshire Water, Welsh Water, and Severn Trent as well, who were late joining the project but have been supporting us as well. And the other names you'll see on there are the natural coagulant suppliers that form part of the project. And we were looking to really kind of accelerate the adoption of these technologies, to gain insights from other sectors, and to do this comparative side-by-side testing that we'll talk to you about, to really understand the life cycle analysis, so the carbon impact of these technologies, as well as the cost and operational impact as well. And then with that real focus on applicability for small rural sites, but with a relevance to the whole industry. So some of these technologies we've tested in a rural kind of thinking space, but actually they could be applicable for large sites too. It's broken down into 3 work packages, which Callum and John will walk you through and talk to you about the testing sites. And it's a 2-year programme that ran from June 2022, and we will finish in November of this year. So we're just giving you a flavour for the knowledge that we've gained so far without the end of the project being completed. And so I think now I'll hand over to Callum to talk through work package 1. So we'll just swap chairs.
Morning, everybody. My name's Callum Grundy. I'm a senior process engineer at United Utilities. I've been involved in this project right from the concept, bid delivery, and right through the delivery of the pilot plant. And now we're into sort of report writing and dissemination. So I've got 15 minutes per work package to take you through 12 months worth of learning. So it's going to be quite fast paced, but please bear with me. I'll do my best to talk you through it. So the electrocoagulation work package, this was our work package 1. This was a side-by-side trial of 4 electrocoagulation suppliers for a period of 12 months. And you can see those supplier names across the top right of your screen. So that's Kalina, Power and Water, Hydro, and Evergreen. And going into the project, we were aware that a number of water companies across the sector had done some of their own very short-term electrocoagulation trials. But what we felt was missing for the water sector was a real view on the O&M, the operation and maintenance impact of this technology. And with that in mind, we went for a 12-month trial. The technology itself, if you're not aware with electrocoagulation and how it works, If you think back to sort of GCSE chemistry, it's basically a couple series of electrodes, a cathode, an anode, and you pass electric current across the plates. And the anode is sacrificial, constructed of iron or aluminium or any other metal that will coagulate. And essentially, you are dissolving that plate in situ. So rather than dosing liquid chemical in the form of ferric sulfate or similar, you're generating it in situ by kind of depleting a metal plate. Photos that you can see on the right hand side of the screen. So in the top right, you can see there's quite a lot of high vis in that, but this was one of our open days that we hosted down at Woolton Wastewater Treatment Works, where we've had a number of those during the trial, where we've invited water companies, so both partners, advisory members, and even water companies who aren't involved in the project, to kind of share the knowledge and come and learn about the technology. And then in the bottom right of the screen, there's a couple of photos of what some of the rigs look like, and there's a few more photos in some later slides. In terms of what we were trying to learn from the project, there was a big focus on process performance. So does it work? Does it remove phosphorus? What's the ion residual like? We had a focus on influent criteria. So are there specific conditions which make the technology work better? So one of the things that we'll talk around is conductivity and different kind of feed locations that we tested to kind of try and work that out. OPEX, this has been covered a few times, but this is essentially electrocoagulation versus chemical. It's a question of power consumption and plate replacement versus cost of chemical. So the OPEX consideration was something we wanted to take into account. Our carbon assessment, that's currently being carried out at the minute. So we're doing a lot of work around the carbon numbers. And there's some of the other things that has been mentioned by Lisa as well, in terms of risk mitigation. So can we de-risk the technology? Can we get over the hurdles that our delivery partners kind of highlighted to us previously? And we wanted to do that by kind of capturing some real operator knowledge on site. Our pilot plant ran from March 23 to May 24, so just over 12 months worth of trial time on site. The trial site itself was Woolton Wastewater Treatment Works. So for those of you not familiar with UK geography, that's in the south area of Liverpool. And it's a reasonably sized wastewater treatment works. It's only 40 meg wastewater treatment works. So it's not a rural wastewater treatment works, but what it does enable us to do is to take side streams, so take a proportion of the flow and run that through an offline pilot facility. And we actually hosted work package 1 and work package 2 on the same site. So up the top end of site, you can see highlighted here, this is where we had our electrocoagulation pilot area. And then down here, so to the left of the site, is where we had our natural coagulant trial area as well. And so part of the reasons why we chose Woolton were because it doesn't currently have a phosphorus permit, which means that it doesn't dose chemical, which means that there is phosphorus available for us to remove throughout the site. And it's also pretty much 100% domestic, so there's very little trade coming into the site. So we thought quite representative of what we would see out in a rural wastewater treatment works. So on your screen, you can just see a timeline and some photos from left to right in terms of sort of where we started and where we ended up. I'm not going to talk to every single date and milestone on the screen, but essentially we picked an area of site and we transformed it into a pretty impressive pilot facility. So the photo in the middle of your screen, you can see there's 4 electrocoagulation suppliers side by side, and we also had a control lane which dosed ferric sulfate. We tested a number of different dose locations throughout the trial as well. So we started off with humus effluent on the recommendation of the suppliers, because that was the least loaded up in terms of solids, so potentially the most efficient for the chemical reactions to take place. And then we gradually moved it upstream. So we moved it upstream to coming up directly off the trickling filter, so humus feed. And then we also did a period of testing where we dosed some salts to raise the conductivity, and I'll come on to that in some later slides. So the next few slides, there's a lot of graphs and a lot of data. It might be quite busy, so I'll do my best to talk you through it in a short space of time. So straight into the performance data. So on the screen, it is a busy slide, but I will talk you through it now. So we've got a 6-month snippet of final effluent data from our pilot plant. So this is phosphorus data, which has been collected from our Phosphax instrument. And it's worth bearing in mind that upstream of those Phosphax instruments, there was a TMS filter, which was around a 10 micron filter. So there is an element of solids removal upstream of these phosphorus results. Now, one thing that you probably notice is quite erratic. And one of the things that we learned from the trial is that the performance was quite up and down for a period of time. I'm just talking through the legend as well. So the orange that you can see sort of consistently less than 0.5 is the ferric. Kalina is the dark green colour. Evergreen is the sort of dark blue colour. Hydro is the sky blue. Power and water is the pink. And then our feed is the purple line at the top. Now, around this period here, we were going through quite a lot of, I would say, optimization work. And you can see that in the results. They're very up and down. Around the turn of the year, particularly for a couple of the lanes, and you'll see that in the green and the pink, the Kalina and the power and water, we did kind of get to a point where we thought we'd optimize the systems, and we started to see more consistent performance. And you will see that sort of from this period here to the end to the rest of the year, the power and water and Kalina and the ferric were pretty consistent in terms of effluent quality on the instruments. Unfortunately, the evergreen system, we didn't really get any sort of consistent performance with that one, and we think it was down to just kind of being undersized, just not enough power to the unit. And hydro, you'll see that there are some spikes of good performance, but it's very quickly followed by sort of spikes of poor performance again. So that we didn't quite get there in terms of stable performance with hydro, but we did see it for some short periods of time. Now, this graph is quite interesting. So the left-hand graph that you'll see here, this is percentage removals of phosphorus. So the graph on the left-hand side of the screen that you'll see, this is laboratory data. So this was coming directly off the settlement lamella. So directly after each electrocoagulation technology, we had a settlement lamella for solids separation. And the right-hand side of the screen is based on the instrument data, where there was some additional solids capture. So purple, dark blue, and light blue represent the different testing periods that we did. So humus effluent, humus feed, and then humus feed plus salt dosing. And then we've got the individual lanes along the bottom of the screen. So ferric, Kalina, evergreen, power and water, hydro, and that's repeated on the graph on the right-hand side. Now, what you'll see that when we looked at laboratory data, which was coming directly off the back of the lamellas, the ferric dose lane was consistently the best in terms of phosphorus removal, although there were some suppliers that were not far behind. When we moved across to the instrument data, those two suppliers caught up, which kind of tells the story that we think there was something in the solids, and the solids data kind of does back this up. The ferric dosed solids did settle better than the solids that were generated on the back of the electrocoagulation lanes. Not quite sure why that is, but it's something to kind of investigate as further work, potentially looking at the mixing efficiency, or we're also aware that hydrogen gas is generated from the EC lanes, and we think that that could potentially be adding a bit of flotation at the release point. But with solids capture, we think we can get kind of comparable performance with the electrocoagulation as you can with the ferric. That's the key message. I can't talk about phosphorus performance without talking about metal residuals. So on the y-axis on the left, these are your iron concentrations. Y-axis on the right is your aluminium concentrations. Everybody used iron, apart from hydro, who used aluminium plates. And you'll see that there's a period here where hydro was actually offline for a period of time. But the key message here, and potentially a risk associated with electrocoagulation, is the levels of the iron carryover that we saw. This should be taken in context of pilot plant equipment as well. So this is not kind of fully designed equipment. It's temporary hire kit, it's pilot scale. So it should be taken in that context. But we looked at the ferric lane, which is the orange, which again, even that is still hovering around the 4 milligram per litre, which we would typically be permitted for in the UK. But when you look at the electrocoagulation lanes, so the power and water was very high, and the iron residual, the hydro lane was quite high in the aluminium. Kalina was actually quite close to the ferric, but still risky. And then the evergreen was was low on the iron, but that was mainly because it wasn't generating much iron initially due to kind of issues with the design. So that just needs to be highlighted in terms of a potential risk. So something else which is very important for electrocoagulation, and that is power consumption. So this graph here, if I talk you through the colours again, and apologise that these are quite busy, but we've got lots of data. So the blue graph that you can see is the evergreen power. The orange one is the ferric, green is hydro, red is Kalina, and purple is power and water. And when you consider the P removal performance in combination with the power consumption, it's something that would need to be considered in the context of a rural wastewater treatment works. Not all of these treatment works will have a massive power supply. They might need power upgrades. So this would be a major design consideration when considering electrocoagulation. And the key thing to consider on this is look at the variability between power consumption between the different rigs. Some of the lanes were kind of quite close to the same power consumption as the ferric lane, and the ferric lane was only using the dosing pump. But the power and water lane was actually quite close to the ferric lane in terms of power consumption. It was quite efficient. On the flip side, we had the Kalina, which also had very good P removal, but the power consumption was significantly higher on that lane. But then when you kind of consider the iron residual was lower on the Kalina lane than it was on the power and water lane, there's kind of a lots of different things to consider in terms of how you would select a potential technology going forward. And I imagine it would be very site specific and permit specific. But this is just to kind of illustrate the variability in power consumption. And you can actually see when it drops when rigs were on and offline as well. It's quite a good representation to show that when units were on or offline. So you can see the hydro then was off for a while, and that was related to a hydrogen issue that I'll come to in the next few slides. So with that in context, this graph here is trying to show an efficiency in terms of milligrams per litre of phosphorus removed per kilowatt consumed. And this does need to be taken into the context of which lanes were removing significant amount of phosphorus compared to those which weren't removing much. So evergreen looks like it's reasonably efficient compared to Kalina and hydro, but in the context of performance, it wasn't removing much phosphorus. So it is skewed a little bit. You will notice that the ferric lane looks a lot more efficient, and that is because power is not really the true measure for ferric dosing in terms of the comparison on OPEX. What we really need to do is kind of convert this into a pounds, so milligrams per litre removed per pounds spent on OPEX. And when we do that, I imagine that the ferric lane will come down a bit in line with these, but we included this for completeness because it was our control lane. One thing that you will notice on these graphs, and I've mentioned this, is that we did a period of salt dosing, and the reason we did that is because on advice of our suppliers, our EC suppliers, the conductivity has a significant impact on electrocoagulation performance. You increase the conductivity of the water, you increase the efficiency of the electrical transfer, which basically means you get more bang for your buck in terms of power consumption and P removal. And you will see that when we moved from the period of standard operation to the period of operation with salt dosing, that you do get an increase in efficiency. So we got more P removal per kilowatt consumed. So that's something which is kind of really key to point out. The other thing that we should consider is how much pain and effort it was to kind of keep that salt dosing system operational during a pilot plant, and whether you would actually consider a full-scale salt dosing system would be up for debate. But one thing it does highlight is the importance of conductivity. So this is just a summary of some other key learnings that we've learned from our time on site with electrocoagulation. So there's a number of different points kind of highlighted on the screen, and I'm not going to go into all of them in detail. Some of them I've already covered. But one thing that does need to be highlighted is the hydrogen generation. So at the surface of the plates, when you get the reaction, you do get hydrogen gas generation as a byproduct. And we actually ended up shutting down our pilot plant for a period of time after we detected hydrogen gas inside one of the shipping containers. More a symptom of the pilot trial, because it was in shipping containers. In reality, it might be on a skid, but we did have to conduct a full DESIR risk assessment. We had to install additional forced ventilation and monitoring inside the shipping containers. And we did share that learning with the rest of the water sector, and subsequently as well, one of the suppliers has even modified their design to kind of mitigate that risk as well. So at the time, it felt like it was something which was, I don't know, it wasn't necessarily going too well with the project, but we've managed to turn it into a real good learning point, and the suppliers have even kind of picked up on that learning and adopted their designs. So it was a real good piece of learning from the project. One of the other things that we've learned as well is the designs vary quite significantly from supplier to supplier. Try to show that in the photos, but you'll get some electrocoagulation plates which require lifting gear to be pulled in and out of the reactor, and you've got some which are handheld, and the difference is that they just simply last longer, they last shorter. There was also other designs, sort of a concentric design with the plates as well. So this is the hydro design with this cylinder here. This is the Kalina, the bottom right. Evergreen was very similar to this. And sort of the big plates that require lifting gear is the power and water design. And they've all got their own pros and cons, depending on the site-specific requirements. I talked about power, but power is a key consideration, especially when you're considering these rural treatment works. The impact of salts, I think I talked about that on the previous graph, but the key thing is conductivity is something which is really important to kind of understand on any target sites for electrocoagulation. The metal concentration, the residual, is something which needs serious consideration. Whether you would probably need some kind of downstream protection for that in the form of a tertiary solids removal piece of kit. And then I guess on the plus side, we found that the electrocoagulation does not consume any alkalinity. So when you can compare that to ferric and what Lisa was alluding to earlier with alkalinity correction and carbon impact as a result of sort of caustic dosing, EC doesn't do that. So there's a real benefit there as well, particularly on sites where you might need it on a ferric dose solution. So this is just a summary slide. So potential benefits and risks are highlighted here. So we have talked about it's a chemical-free pea removal system. It doesn't consume any alkalinity. The EC itself has quite a small footprint, and it could be applied in a modular approach. There's no requirement for chemical delivery areas, blind tanks, chemical storage tanks, and the associated health and safety impact with storing chemical on site. And quite often, the chemical comes in with lots of other impurities. You don't get that with the electrocoagulation. On the flip side, there are a few risks and barriers that we've highlighted as part of the project, which would need to be considered. So we talked about the high metal residual. The power consideration varies from supplier to supplier. Passivation, so that is the fouling of the plates. So as you run electricity through the plates, you get a layer of oxide and hydroxide layer forming on the plate surface. And essentially that increases the resistance of the plates, which basically puts your voltage up until it gets to a point where you would either trip on power or you would need to replace your plates. So that's something which needs to be considered in terms of plate life. We talked about the scale. So at the minute, we think it's only really applicable to sort of small rural wastewater treatment works. And that's mainly because there's a tipping point where the power versus chemical cost will just become unsustainable. And then, yeah, DESIR consideration is a big thing to think about as well. Overall conclusions. So EC, it does remove phosphorus without the need for chemical. But we believe that for permits, probably less than one, you would need TSR as well because of that iron risk and because of the poor settling solids that we observed. Yeah, and I've mentioned the metal carryover a few times. In terms of next steps, so there's a few things that we didn't manage to test as part of our trial, but we've subsequently learned about their importance. So we think there's some further work to be done to consider the impact of things such as ORP and aeration. Potentially some further work to be done in combination with TSR to see can we hit low P when we combine it with those two technologies. Cost and carbon evaluation is something which is ongoing and will be shared in due course, but we're doing a lot of work in the background on that. And I guess in terms of the UK water sector position, several water companies have placed orders for electrocoagulation on some of their sites, and they've all been to site to kind of have a look at our trial, share our learnings. We've had knowledge shares online as well. So a real kind of positive outcome for the wider water sector in terms of that knowledge share across the wider water companies. And there's something which I'll cover in the next 15 minutes is whether there's any potential to combine electrocoagulation with some of the other approaches that we've tested. So that takes me on to work package 2. I'm just going to grab a quick drink. Yeah. So our second work package was based around the use of natural coagulants. So these are bio-based coagulants or plant-based coagulants, and Lisa alluded to this earlier, but this part of the bid, this work package, was really developed out of a piece of work that we commissioned our utilities to complete for us a few years ago, whereby they conducted a horizon scan of chemical-free treatment opportunities across the water and wastewater treatment process. And one area that they focused on was natural-based coagulants for pee removal. So we took their shortlist and we got in contact with a number of the companies that were listed as potential suppliers, and we reached out to them. We talked about the project, and we convinced a number of them to get involved in the project to see, what could we do. It was a bit of R&D. The plan itself, it started off with some lab scale testing. So we did a lot of work doing jar testing in the labs. There was 5 different products which we were supplied to us, which you can see the table in the bottom left. So we started off doing some work in the lab, and we assessed each of the products on their own. So we dosed them on their own without supplementing with anything else, just to see, did they do anything for phosphorus removal? And what we found was some of the products were really, really exceptional at solids removal. What they weren't so good at is pee removal. So we didn't want to kind of cut the testing short at that point. We thought there was something in the solids capture that we could potentially benefit from in the whole context of pee removal. So we actually came up with the idea of can we combine the products and take advantage of that solid settlement? Can we combine it with ferric sulfate or similar to get an overall reduction in metal-based coagulants? So rather than completely removing it, can we reduce it? And when we did that combination, the results were really fantastic. And there is a YouTube video actually which shows a live jar test. So if anybody's got 5 minutes and they want to watch a jar test after this, there'll be a YouTube link posted in the chat. But the video speaks for itself. But what we found when we did that combination is that they really kind of had a synergy. They really complemented each other. And we managed to actually cut the amount of ferric sulfate that we've required by around 50%. But the real interesting learning was the impact of the natural coagulant on the iron residual. So the iron residual was really, really low. So it was compliant, basically coming out of the jar tests. So on the back of that learning, we shortlisted the 2 most effective products. So they were a product was produced by BWAT in Spain. It's called Servi. The company is called Servi Eco. The product is called BWAT. It's supplied to the UK by Acorn Water. And then there was also the Hydrex product, which is supplied by Veolia. On the back of that learning, we took the jar testing results, and we basically designed a pilot plant almost to scale up a continuous jar test. That was kind of the thinking behind it. So we ran pilots testing, and now we're kind of in the reporting phase, and some photos and jar tests there, but the video really does it justice if you get time to watch it. In terms of timeline of events, I think we actually spent sort of around 6 months doing a lot of lab work, a lot of jar tests, a lot of data. But once we kind of concluded that, we scaled up to a pilot plant on site, which looks something like this in the top right. And I think I've actually got a flow chart in the next diagram, which kind of brings it to life a bit better. But we had a lot of sort of started commissioning on site, so about August period 2023. Ran our pilot plant for around 6 months, and then we finished sort of winter time last year. So this is what the pilot plant looked like. Quite simple. I'll talk you through the flow diagram at the top. So we took screened crude wastewater from the Wilton inlet channel, so it's down here, and we pumped it through a pipe flocculator. So that was to promote some mixing, and the flocculator had a series of injection points. So in our control lane, we dosed ferric sulfate, and in our experimental lane, we dosed ferric sulfate plus natural coagulants, so that's the BWAT, all the Hydrex, and then we settled it. So we tried to replicate what would a dosing system, a simple dosing system, look like in a primary settlement tank. So a bit of mixing and settlement. And that's what the kit looked like there. So temporary higher flocculator, temporary higher settlement lamellas from Silkbuster. And then this is what the product looked like. And without the labels, you would be forgiven for confusing the two because they do look very, very similar. And that's because of the tannin content that's in the natural coagulants. They have kind of a strong tea type colour. So straight into some results. There's lots of results to share. And again, these graphs are quite busy, so I'll just kind of talk through. So the left-hand side of the screen, so with the green is the BWAT performance, and the purple on the right is the Hydrex, and that will be consistent for the next few slides. So BWAT on the left, Hydrex on the right. So this is looking at phosphorus performance. And in each case, we've got the feed in the dark blue, the control for the ferric lane in the orange, and the experimental data in the pink. Now, what you'll notice here is we started off very, very well with the experimental lane, outperforming the phosphorus, and then we had a period of kind of gradual deterioration. What actually transpired is that we had some issues with the flow meters on our pilot plant, which meant that the dosing was out for a period of time. But this is the raw data. So the performance is quite inconsistent for both lanes on this one. But I guess the key thing is they follow a very similar pattern. There's not much detriment to the performance. And I should have mentioned, I forgot to mention, that our experimental lane is using half the amount of ferric sulfate supplemented by the natural coagulant. So in each of these cases, the control lane is using a 4 molar ratio of ferric sulfate, which is what we found from the jar tests, to meet a target of 1 milligram per litre P. So that was from the jar tests. And then the experimental lane used half of that amount of ferric supplemented by 100 ppm of the natural product. Should have mentioned that at the start. Now, what you'll see in the graph on the right-hand side, this is the experimental lane which uses the Hydrex. You'll see that even with 50% of the amount of ferric supplemented by the natural coagulant, the performance is pretty much identical. Now, this was never about how low can we go with P either. The initial kind of proof of concept was, can we get the same performance on P removal when we use 50% less ferric if we supplement it with something plant-based? So it was very much a proof of concept. Suspended solids performance. So again, the left-hand side is the BWAT, the right-hand side is the Hydrex. And what you'll see is the experimental lane, pink, outperforms the control lane, so the lane that is dosed with ferric on its own, pretty much consistently. Some of these numbers are very, very low as well, considering that we're dosing it with the screened crude. So this is 25, this sort of bottom line here. Some of the results are less than that. Again, there was a bit of a wobble in the middle when we kind of lost our control on the flow meter. But you'll see something very similar with the Hydrex as well. So the pink line is consistently outperforming the orange line. So the impact of the natural coagulants on suspended solids is pretty good. Some of these were crystal clear coming off. Some of them look like fine effluent. Now, the real interest in learning, and you'll see it in this graph, is the impact on the iron residual. So the feed iron is the blue, so pretty low coming in, as you'd expect, not much iron in the catchment. The control iron, so this is the lane where we dose ferric sulfate, the iron residuals were quite high and quite erratic. But in the experimental lanes where we've supplemented it with natural coagulant, you'll see that the iron residual is pulled right down, quite often below 4 milligram per litre, which is where we're typically permitted. And bear in mind that this is kind of in a primary dose application, so we'd have further buffering downstream throughout the wastewater treatment process. So the key benefit to the natural coagulants, we feel, is the impact on solids management and particularly iron control. There's a few other percentage removals here in terms of other things that we monitored. So we've kind of got our control lane percentage removals on the left, and the experimental lane percentage removals on the right-hand column. And I've highlighted for ease the ones which kind of outperformed throughout the different measured parameters. And you'll see that a lot of the highlighted columns are on the experimental lane, so the lanes where we dosed with natural coagulant. So not only did it outperform for solids and iron, which I talked around, it also outperformed for BOD and COD as well. There wasn't much impact on ammonia. And yeah, the ferric was probably slightly better on its own, but not kind of significantly better overall. Now, I mentioned this in the previous work package when I talked around the potential to combine approaches to phosphorus removal. So if you cast your mind back around 20 minutes when I was talking about high iron residuals from the electrocoagulation and the learning I've just shared in terms of the benefit of natural coagulants pulling the iron residual down, we thought there was an obvious combination that we should try. So we actually did a very, very short trial at the end of the project where we dosed some natural coagulant into the flock tank in the power and water rig to see if we could control the iron residual better. And bear in mind, some of the iron results were kind of in the high teens on the power and water lane. You'll see the bottom left is the iron, the effluent iron when we added the natural coagulant. So you can see here it was 20 before we added it. When we added the natural coagulant, it was consistently less than 4. And the interesting thing is the graph on the bottom right, this is power consumption on the power and water lane. So this is kind of consistent with the dose rate. What we found was when we dosed it, when we supplemented with a natural coagulant, we cut power consumption by 75% because it enhanced the effects of the iron that was generated from the plates. We also saw some benefits in terms of pea removal, top left, and solids performance, top right, but the real key was controlling that iron. So just to summarize some benefits, risks, conclusions, and next steps. So the benefits of natural coagulant, so the obvious one is the improved impact on iron residual and solid performance. There's also slight betterment on alkalinity consumption. So on sites where it might be borderline, if you reduce your ferric and supplement it with natural coagulant, you might not necessarily need to implement caustic, although we do need to collect some more alkalinity data. Potential to remove that load on downstream assets if you dosed it sort of in a primary application, reduce reliance on ferric sulfate, and we're still doing this work, but we think there's a high possibility that we will reduce operational carbon. Now, one of the risks or barriers that I haven't mentioned yet is the requirement for EA approval to use these products at scale. So we have been negotiating with the Environment Agency at a national level, so on behalf of the whole UK water sector for a while, so that we can start to move some of these natural coagulants towards full-scale trials. We've had to provide a lot of evidence and third-party opinions on the products to get anywhere close to an EA approval, but we think we're almost there. And as I said, that will be done on behalf of the whole UK water sector. Something that needs to be pointed out, so from a unit cost perspective, these are more expensive than ferric sulfate. So a full kind of cost benefit analysis needs to be done on the wider impacts across the wastewater treatment works. We certainly feel if you're putting it in as part of a new build solution and you could design it in instead of mechanical equipment for ion control, then it would save you a significant amount of capex despite the increased OPEX. LCA and sort of sustainability impact is in progress. So these are derived from plants which are produced in temperate climates. So there is some shipping involved, which needs to be considered. And the other consideration is the security of supply. So at the minute, there is limited volumes available of these products. So that's something to consider and potential scale up. And there's also additional storage requirements. So yes, it's another product. It's another tanker. It's another tank and dosing system that you require on site, which needs to be considered as well. And another key learning that we noticed is when you don't quite get the mixing right, or you don't get the dose combination right, there is an impact on colour. You get like a blue-black type colour, which we don't think has any impact on performance, but it is kind of visible to see. So overall conclusions, so the natural coagulants offer an excellent option for solid and ion control. And when you dose it in combination with metal-based coagulants, there's a method of reducing that requirement. In terms of next steps, we think there's some further work to do to determine how low we can actually drive the phosphorus. So we only really ran at the 2 molar ratio plus 100 ppm. So there's a number of different combinations that we need to test out to really understand how they interact with each other. I've talked around the work that we're doing with the EA for the wider water sector. And there's also some further testing to be done with other products such as ferric chloride, aluminium-based products as well as dosing at various points of application in the wastewater treatment process. We do want to move towards some full-scale trials as well, and we're also aware that on the back of some site visits and knowledge shares that we've done, that other water companies are also taking a real keen interest in this and doing their own work as well. And on the back of the very short trial we did combining the electrocoagulation and the natural coagulant, we think there's a real kind of massive game changer there in terms of bringing the technologies together and potentially coming up with a winning combination to meet low P on rural wastewater treatment works. So I think that concludes my part, and we're on for a break now.
Thanks, Callum, and thank you to our presenters so far for a really great presentation. And we've had some really great questions in the chat, so do keep popping those in. We're just going to go for a quick break now, so we're going to take 10 minutes for everybody to grab a drink and just have a little break. So the time is now 3 minutes past 11. We'll be returning at 13 minutes past to hear some more about work package 3 and some more lessons learned. So 11:03, we'll be returning at 13 minutes past. Thanks, everyone. Hello and welcome back, everybody. So in just a minute, we're going to be going back into the presentation to hear from John and Callum about work package 3. And then we'll go into some more lessons learnt, followed by the Q&A. So do keep popping your questions into the chat. Callum, are you around and ready to pop your camera back on?
I think this is just John. I'm going to do the summary at the end.
Oh, amazing. Okay, sorry. John, go ahead.
Thanks, Leah. Okay. Well, good morning. John Williams from the School of Civil Engineering and Surveying at the University of Portsmouth. I'm going to talk about work package 3. And this has been delivered in conjunction with Southern Water. Della Martin was our project manager, and work's been done mainly by Jean Robinson, working on the project as a research fellow, supported by Candice Cameron. The reactive media work package 3 was building on some work we've done previously with Southern Water through PhDs and other studies into some of the mechanisms around reactive media. Also, of course, lots of water companies like United Utilities have experience of using reactive media. What we were trying to do through this work package was, one, look at if any new reactive media have emerged, which either had improved performance or had avoided some of the issues around elevated pH, which have been seen in other studies. Also to try and standardize the testing. There's been lots of testing done on reactive media, but these have been done on different scales and different wastewater, some of them synthetic wastewater, some of them real. So trying to come up with a standardized way of testing, and then move on to some field testing and looking at a containerized system which can be moved between sites with different water chemistries, which can affect the performance. The second work stream was all around trying to work with partners to come up with some standardization of engineering design and deployment. How would the reactive media be deployed, and what locations, and what would be the operating parameters around it. And finally, some cost modeling, trying to understand where reactive media sits in comparison, say, to ferric, and in terms of different configurations, different replenishment rates, and so on, and how that might affect the economics and where that leaves the technology. We've been doing most of the work on site, on real wastewater treatment sites. We have a field station at Petersfield Wastewater Treatment Works, which we rent some buildings and outside area from Southern Water. At this site, we've got an innovation hub with Southern Water. We work on lots of R&D issues, and we also work with the supply chain SMEs. The beauty is we can run pump supplies from the wastewater works and run large-scale pilot rigs. We have on-site labs to test. So that's the facility we've been using. If we move on to what we actually did in the project, here's the timeline. It's all on my screen. So here we can see in September 22, we've started some column testing in the lab, and we're also doing some outside column testing with faster rate media. And then moving through, we've moved to set up our containerized rig, and that was set up at another wastewater treatment works close by, a place called West Marden. And then finally, we're moving through to the latter stages of the project now and the project reporting. So in terms of the trials, the first one, we're looking at the practical trials. The first thing we did was do a large media horizon scan, and we looked at, we collated about 20 potential media, and then we went out to industry, the partners and beyond, to survey what would be the most appropriate media, what criteria should be applied, and we had a scoring system which actually ranked different media in terms of their interest to the water industry. We ended up deciding to split this into two. One was low rate media, so generally media which have got a higher hydraulic retention time, and the media which was scoped in were Phosgrain from DTI, Phosflow supplied by PET Limited at the time. And I've been working with some MSc students over the years on producing calcined cockle shells as a reactive media, and that was the circular economy aspects of that appealed to the partners who were scoring it, and so that was selected for low rate media studies in the lab. And we set up columns with 3 different empty bed contact times of 6, 12 and 24 hours. And the site we were doing is at Petersfield. We were running with final effluent from the works, but as there's already dosing phosphorus removal on site, we had to dose up the effluent. So we dosed the effluent up to about 10 milligrams per litre P for these column trials. And externally, the high rate media, we had 4 media selected, the GH101, bio-free, catalytic carbon, cannabis, and we ran these in outdoor trials at much shorter empty bed contact times of 2.4 and 7.2 minutes. And again, this was with FE dosing. We decided to use empty bed contact time rather than doing it per specific mass or specific surface area, so that we were actually comparing volume per volume, because of course that's going to be, if these are going to be deployed in a filter or wetland or some other type of system, it's the size of the system which would be most appropriate for design. The high rate columns, let's talk about the high rate columns first. These were outside, these were pumped with final effluent which we dosed. This trial was very difficult because we found the chamber we were pumping from seemed to accumulate solids, and we seemed to be fighting an ongoing battle against suspended solids, and I'd come up with various filtration methods and eventually a sacrificial reed bed to try and handle these solids. We had some good results. Maybe the DEI media was performing the best over the longest time, but we had a real problem trying to control the flows and control the backwash on this. We also, I mentioned a bit, we had an engineering design workshop with the water companies, and actually the water companies who were there actually scoped out and said this wouldn't be the application they'd imagined for reactive media. So we completed this trial and didn't take it any further. In the lab, on the low rate media, we were working at 6, 12 and 24 hours empty bed contact time based on the previous results. We hit an issue straight away. The cockleshell media, which had performed very well in the lab with a synthetic wastewater, when we put it in, when we started pumping the real Fe through it, the performance wasn't anywhere near as good as we saw in the lab. So you can see that purple dot line at the start of the trial, and we abandoned that because it was just not working. We moved over, replaced it with the Phosphorus. In the meanwhile, there was that had originally been scoped out because the water industry were worried that it was related to the Phoslock technology, also marketed by that company. They were worried about a couple of the elements in there. It turned out actually this was a different material. Actually, it was the Poseidon pellets from Wastewater in the USA, which was being marketed in the UK as Phosphorus. And so we replaced the cockle shells with the Phosphorus, and we can see here we've carried on these columns being monitored regularly for over a year, and we can see that we've got both the media, the Phosgrain and the Poseidon pellets, both performing very well. We've got some increases here. We can see that after, I'm afraid my screen's showing this in very, very small. After about 200 days here, we can see the 6-hour empty bed contact time for the Poseidon pellets going through. And if we look at the results for both these media, we were getting getting much higher uptake rates than we've seen in various other commercially available media we've trialed in the lab. They are a little bit smaller, so they might need a little bit more solids protection, but that means that they would be able to operate for longer periods in the field, or maybe the media, the beds could be sized at a smaller rate. But most interestingly, on the right, on the left here, just look at it. Nearly all the media which are available on the market in a granular size for a filter tend to increase the pH above limits for discharge, and that requires an additional stage. You've been using carbon dioxide dosing to bring the pH down. But with the Phosphorus stroke Poseidon pellets, after the first couple of days, the pH for these media was well below acceptable limits for discharge. So we think through this column testing, we've established 2 media which have superior uptake rates, uptake capacities than lots of the media which have been trialed before, and also a media which avoids having the extra pH amendment stage. So the next stage for this project was the containerized trial. The concept behind this is if we've got a container which is equipped with test rigs and online instrumentation, then this could be placed at any sewage works with different water chemistries, and we can test different media and assess their suitability for different deployments. So within this container, we've got 3 columns. And again, we went out to the stakeholders, and we built these 3 columns up. The 3 media we started within the lab trials. There's still about whether we should put some of the more the media which have been used in practice, but then the thought was that these have been tested to quite significantly in the field. And also on the right here, a medium-sized filter, about 600-litre filter, which we filled with the Phosphorus stroke Poseidon pellets. And all of these are linked up to telemetry, phosphates units, total P, soluble reactive P, turbidity and pH, and so on. And this is all connected up through the whole range of the Clarios system to give us continuous readings. I'm not going to go through the results. We haven't processed all this data yet. We've actually found the container to be quite a demanding platform. Lots of we found the pumps. We found that the analyzers have needed more care and more attention than we originally envisaged. But we are getting good results. We need to process these. There's been some interruptions of flow through the works as well. The works has no flow at times, and that can trip the system out. But we have got some very promising results coming through from these trials. The other strategies we've been looking at, one was the engineering design. We held a very interesting workshop hosted by Stantec in Birmingham, where we had 15 attendees representing 8 water companies, and probably overdid the sticky dots on the flip charts. But we really had a whole day's discussion about how this might be deployed, what might be the population size ranges, what might be the characteristics of media which would be most appropriate, what about replacement, what about recovery and pH adjustment. And this is going to feed into, alongside the testing, a code of practice as an output from the OFWAT project for the use of reactive media. And I mean, there's quite a few questions moving forward, but one key one is the cost modelling. Although these media we identified through this trial may have superior performance characteristics, they are more expensive than some of the other media on the market. We tried to organise a cost modelling workshop, but we had much less interest in this than in the engineering design workshop. And so we've been working with our water company partners, United Utilities and Southern Water, and some QSs from my department, Tom Woodbury, to come up with some cost models for comparing reactive media in different size beds with different replacement media with ferret costs. We're currently, that's still ongoing. We've got a first principles cost model to look at filters in wetlands, which we're currently putting in costs in to come up with estimates of where reactive media sits versus ferret. And of course, ferret isn't just the actual dosing equipment. There's some interesting data in some of the water company reports about the other externalities, which Callum and Lisa have mentioned previously. So in conclusions, we can get very low P consents with reactive media. We've got some media which are performing very well, do not require pH adjustment. Costs is going to be the deciding factor, as is solids management. Obviously, small works can have occasional issues with solids carryover. And so we need to work through as well with these cost questions about what replacement periods might be appropriate, and in the longer term, how P might be recovered. The container was a great demonstration of the engineering potential, but at the moment is requiring a bit more tender loving care than we imagined. Just as an example on the right here, this is from a previous study we did. We can see some reactive media in SEM. We can see the deposits on the surface. At the bottom, we've got an SEM EDS scan section through, and that green line around the outside is the phosphorus deposits on the outside of the media. So trying to understand this and trying to understand the way it's bound and the way it can be recovered is obviously a key point for the circular economy and addressing phosphogeddon in the future. I'll hand over to Callum then.
Oh, slides have disappeared for me. Is it possible to reshare them, Leo?
Oh dear, did I press something?
Sorry, bear with, let me just get you to the slide we were on.
Sorry, I'm not used to Teams.
No, you're fine, John.
Yeah, they're back for me. Just flick through quickly. Okay. So this is just a summary slide really to kind of wrap up everything that you've heard over the last hour or so. Appreciate there's a lot of information that's been kind of put together in a very short presentation period of time. But before I kind of wrap up, I just want to say a massive thank you to our process technology team at United Utilities. They've helped us to kind of design, implement, install and operate both pilot plants down at Woolton for 12 months in all weather conditions, freezing cold winter. We had lots of snow over the winter as well, and without process technology team, we wouldn't have had the amount of data that we've collected to kind of land these conclusions. So just wanted to give them a big shout out because they've been invaluable to this project. Just in terms of the summary then, so work package 1, the electrocoagulation. So the key takeaways from electrocoagulation. So it does remove phosphorus, but there are a number of other considerations to think about. So namely high metal residuals and potential requirement for downstream protection. The conductivity has a significant impact both on power and performance. So that would be a key characteristic that we need to consider when we're evaluating sites. And the hydrogen gas, which is generated as a byproduct and requirement for disease risk assessment. Work package 2, so the summary or the key takeaways from the natural coagulants. So we found that they enabled us to reduce, not remove, ferric sulfate requirements, but by up to 50%. And the key benefit is really around the solids management and ion control. They are more expensive per unit than metal-based coagulants, and there is a limited volume and supply chain which would need to be considered. And then just to summarise some of the stuff that John talked about on reactive media. So yeah, the high rate columns proved to be problematic and would not be taken forward or recommended as a viable method for reactive media treatment. The phosphor media looks to be a really promising new reactive media, which has got really good phosphorus performance and little impact on pH. So potentially a bit of a game changer there in the reactive media space. And low P, it can be achieved, but the cost is a key barrier that needs to be overcome. Now, if we just kind of draw you to the right-hand side of the screen, there's some key next steps and key dates that people might be interested in. So our work package 1 and 2, the electrocoagulation and natural coagulants trials, they're both concluded and we're currently very busy evaluating data, results, report writing, and that'll be issued to our steering group in due course, and then it will be available to the wider water sector after that. Our cost and carbon assessments are currently being undertaken, so we don't have anything to share on that at the minute, but we are doing a lot of work in the background, and that will be available when the final reports come out. I mentioned this when I talked about work package 2 previously, but we are exploring potential full-scale applications of natural coagulants being explored, both on a number of AMP7 sites and across our AMP8 programme. So there's a couple of sites in AMP7 that we've got in mind where we want to do some trial work. And there's also a significant number of sites in AMP8 where we think it could be a real benefit. But we are working with the EA to get that approval signed off. And that's just kind of a key message to share with the water sector. If you are interested in using these products, you do need to do that Environment Agency liaison. And work package 3, this will still be continuing to run up until September 2024. We've also got our OP Day, which I think is primarily for partners, advisory members, and some kind of key invitees to the project, which are going to come down at Lingley on the 17th of September, and the official project end date is November 2024. Now, I just want to conclude by saying a big thank you to OFWAT for funding the project, and also to Spring for hosting and providing the platform this morning. So I think that's done in terms of conclusions, and I think we're ready for questions, Leah.
Amazing. Thank you, Callum. So if you could just stop sharing the slide deck for me, Callum, so we can see our lovely presenters' faces a little bit better during this session.
Like that?
Yes, perfect. John, are you still around? Are you able to pop your camera on for me? Perfect. Thank you. Okay, cool. So we've had a lot of really good questions today. So thank you so much to the audience for being so engaged. I'm going to start from the top. Hopefully we'll get a chance to answer them all, but if not, we will be posting any unanswered questions along with the answers from our presenters on our platform alongside the showcase recording, which will go on our platform. So first question, I think, is from Gary. And why are water companies being given such stringent drivers?
Sorry, I think I'm taking that, Leah, but we've just been told our camera's not visible. Don't know if you can see it.
I can see you. It may just be the layout.
I think we're just showing as an icon at the minute. Try turning off and on.
Turn it off and back on.
It's we're on. Apparently, yeah. Oh.
Yeah.
Why are we getting such stringent drivers, I think was the question. Is that right, Leah?
Yes, absolutely.
Yeah, a lot of these drivers are given to water companies in England and Wales as part of our challenge to deliver on the Water Framework Directive. So really looking at improving the quality and ecological status of our watercourses in England and Wales. And then we're kind of looking into the future for the Environment Act, some of the drivers that we'll get in the future around delivering our requirements under the Environment Act. So ultimately it's about improving the quality of watercourses in England and Wales, but we are quite consciously, we know we're not the only contributor to phosphorus in these areas, so we're also doing work. So I talked at the start around UU and other water companies in England and Wales as the kind of owner of catchment land as well, and making sure that where we've got land and farming practices on our areas, we're managing phosphorus runoff into the watercourses and working in partnership with farmers and other land users in the area to try and reduce the nutrients entering watercourses. It's not all about effluents from our wastewater treatment works, it's about working in partnership in our region to try and manage that nutrient balance.
Perfect. Thank you so much, Lisa. The next question is from Tessa. I think it might be one for you, Callum. What size are the small works for electrocoagulation? Is there an upper dry weather flow limit for this technology?
Yes, I think so. For this specific project, we said that electrocoagulation was suitable for works size for 5,000 population equivalent and below. That was on advice of the supply chain. I think there's no technical reason why it couldn't work on larger sites than that, but it really becomes a power versus chemical cost type question. I think anything kind of above that, you would really be spending a lot on your power consumption versus chemical costs. So that's kind of where we pitched it in terms of the project. Now, if I kind of recall the slides that I talked through on where we combined it with natural coagulants, what we actually saw was that we managed to cut the power consumption significantly. So we think not only would the natural coagulant combined with the EC give us some tighter ion control, it also opens up the opportunity to implement it on larger sites as well, because it brings that power consumption right down.
Perfect. Fine stuff. Thank you, Callum. I think next one might be for you as well, from Elaine, who wants to know, how are the phosphorus permits generally set in United Utilities and Southern and Wessex? For example, total or orthophosphate, 95 percentile compliance or annual average?
Yeah, so we're permitted on an annual average for total phosphorus.
Perfect, thank you. And then Stuart has asked, what dosing philosophy was used with the ferric addition? So
it was on the context of pilot scale, so it wasn't overly complex, shall we say. It was quite basic levels of control. I think when I was describing the pilot, I didn't mention that so each lane in the work package 1 was fed a constant flow rate. So we did do a short period of diurnal testing, but for the majority of the trial and the data that I shared this morning, it was all done at a fixed flow rate. The ferric dose itself was just based on the incoming concentration. Then that it wasn't flow paced or anything like that. It was just a fixed dose. So yeah, the results have to be taken in the context of the sort of the basic levels of control that we had as well.
Absolutely, thank you so much. Lisa, did you want to add something to that? No, sorry, I thought I heard you go to speak.
But with your questions to look at what's coming in as well on the laptop.
I didn't know whether to follow on because I think there's a few questions that are coming around the electrocoagulation control.
Go ahead. Yeah, absolutely.
Can answer both off in the same. So yeah, as I mean, each lane was fed a fixed 2 litres per second. The EC itself, it wasn't linked to the incoming P, and it wasn't linked to the flow. It's basically set, the dose is set as a current, and that is fixed, and you can manually increase it or decrease it based on the current. Now, there probably is a bit of further work to be done to really kind of optimize that control with the EC, because there will be periods of time where you are overdosing. When we talk about that iron risk, if we're dosing at a fixed current and putting a fixed amount of iron into the system, particularly overnight when you've got low concentrations coming in, you will be significantly overdosing, which will increase your risk. So there is a bit of further work to be done on EC in terms of optimizing the control.
Perfect, thank you, Stuart. Okay, one for John, while you were doing your part, from Stuart, who would like to ask, what would be the strategy around spent media disposal / reuse? Are there any other constituents absorbed which could complicate disposal?
Well, I'll deal with the second part first. From our work, we've not detected any accumulations of anything which could cause problems for disposal, although some of the media we've tested in the past do leach materials which might limit their application. The strategy for disposal or regeneration or phosphorus recovery, I think, is the area where we need to do much more further work on reactive media. At the moment, there isn't a clear regeneration recovery strategy. There's some work done on physical recovery. There's some work done on chemical recovery. That obviously is a big, an important part of completing the cycle on P and recovering P. We've done some work on physical recovery. We think there are some simple ways of doing it. One of the attractions of the seashells is that, of course, they are used as a soil conditioner already. Some of them come with clear material data sheets. They're used in agriculture. So if there was a way of enriching them with P and then putting that straight back on the land, that would complete that cycle in quite a neat way. Unfortunately, there seems to be a big jump between the behaviour in the lab and the behaviour in the field at the moment, and so that's something we're hoping to look at in more detail. But yeah, a key point of this technology is more work's needed in the regeneration recovery space.
Amazing, thank you, John. I'm not sure if you already touched on this in your previous answer, Callum, but Jeremy has asked, how were the flows to each trial unit controlled?
Yeah, so I can answer that for both work packages. So for work package one, the electrocoagulation, as I mentioned, it was a fixed 2 litres per second per lane. So they all received the same concentration of phosphorus. So we had a reception tank which took a side stream from Woolton, and then that was split 5 ways evenly per lane, and we had flow meters monitoring that. And then on the natural coagulants lane, again, that was a fixed flow that was done at 1 litre per second per lane. We didn't go as far as kind of introducing diurnal flow profiles or anything as complex as that. It was more about can we prove that the technology fundamentally works and has got some potential.
Amazing, thank you. And then Gary has asked, could hydrogen potentially be harnessed and used as a fuel?
Is this one for me as well?
Yes.
Yeah, so we don't think the quantities produced are kind of significant enough to warrant kind of the spend and the infrastructure you would have to put into to harness the gas. So I think it was produced in quite small quantities. So when we did some hydrogen calculations as part of the wider DESIR risk assessment, and what we found was, although the quantities were very small, because our pilot plant was housed within shipping containers, it was a kind of it became a confined space. So essentially the concentration built up over a period of time. And that's where the issue arose, really, particularly overnight when we locked shipping containers up at the start of the trial. That's what led us to kind of shut the trial down and kind of conduct a full assessment and put in some additional control measures. But yeah, on the face of it, we don't think there's a significant enough quantity for us to harness it.
Amazing, thank you. Okay, another one for you, Callum, from Owen is, if some of the EC units dosed at different rates, will your cost per P removal calculation take into account the increased OPEX cost in terms of new plates and replacement costs?
Yes, it will. It will consider all of that. So when I showed the power graph for it was up and down, and basically when it was going up and down, that was in line with dose rates being changed. Each system is kind of restricted on its own. The power draw will be different per system. I'm not an electrical engineer, so apologies if I offend anybody with my very basic description. But each lane had kind of tripped out at a specific voltage, which meant that you kind of limited on how high you can put the dose rate. We didn't kind of give the suppliers any cap in terms of where they should be targeting it. We very much let the suppliers lead us on that. They were the experts at the end of the day. But to come back to the question, that will be taken into consideration, and you will see that in the kilowatts consumed, but you will also see it in terms of how quickly the plate's depleted. So if you kind of run them harder with a higher power, the plates will deplete quicker. So we've got a big log of every plate that's been replaced over the period of 12 months, which will be factored into our overall cost assessment.
Brilliant, thank you. Okay, so a couple of questions for Lisa now. So first one is from Simon, who would like to know, how does the power use in production of ferric sulfate off-site compare with the power usage on-site for EC?
Yeah, I guess that's a challenge for us, really, because we don't currently take into account the power usage for production of chemical. And I guess it links really to kind of where our thinking is around carbon impact and carbon assessment. So we currently don't account for the production methodology for the chemical. We basically do it. We've actually moved to volume-based carbon impact, so carbon efficiency factor times the volume that we using in terms of ferric or another chemical. So we don't currently account for that power usage really in terms of comparing side by side. We probably should do in terms of an end-to-end assessment, but the way we really assess something, so actually the impact on power for us would be an increase in power at the site for use of electrocoagulation, but we need to offset that with all the other benefits that we might be getting in terms of minimising chemical carbon and the management of tanker movements and so on.
Perfect, thank you, Lisa. And then the next one for you is from Anwar, who would like to ask, did you do any CapEx and OPEX calculation for all technologies? And did you consider sludge production for all options?
I'll maybe leave the sludge production one for Callum, but in terms of CapEx and OPEX, yeah, we will be doing the full cost assessment, whole life cost assessment, as well as the carbon assessment for the project. But what we will be doing is doing that later on in the programme. So we needed to really understand what the OPEX usage was going to be across each of the different technologies as we've done that out on site, and then we'll build that into the cost model. And I think John's already talked about how we're developing the cost models for reactive media within the presentation itself. And then I guess in terms of sludge production, that's been a bit tricky.
Yeah, so we went into the trial, we designed our trial with intentions to kind of collect sludge samples throughout the duration, but we weren't able to do that because of the manner that we had to operate the lamellas. We had to operate them with a continuous desludge, so we never really got to a point where we built up a significant amount of sludge within the lamellas. So unfortunately, that's a piece of learning that we haven't managed to capture, and would still be a bit of a gap.
And that's for the EC. What about natural?
It was the same. It was the same for both work packages because we were using the same sort of lamellas. We found that was the best way to run them for the pilot.
Perfect, thank you. John, one for you. So you mentioned solids during your part. What is the max solids concentration in the feed to the reactive media in your experience? Potentially a solids break/removal process might be required in practice upstream of reactive media, which needs to be taken into consideration.
Yes, there is perhaps potential, especially for the smaller media, for solids to be controlled upstream. We've operated some of the larger pelletized media, final effluent straight from a works with the usual variations within there. I think for the finer media, you don't really want to be going much above 10. So really, yeah, an upstream solids control of some kind would be useful. But again, that obviously adds to the capex of and opex of the cost, which is going to be a key criteria. Yeah, the bane of our life, solids with reactive media.
Amazing, thank you, John. Okay, a couple more for you, Callum. So does this data set not ignore the additional performance you would expect across the humus tanks downstream?
So trying to interpret that question. The way our pilot plant worked was we fed it with a feed source. So we started with humus feed, and then we moved up to the other way around. We started with humus effluent, we fed it through the EC rigs, and then we settled it in a settlement lamella. And the idea of the settlement lamella was to replicate the settlement stage that you would have at full scale. So it doesn't necessarily discount the impact of settling, because that's what the settlement lamella was there for.
We just couldn't do that on site at Woolton, so we couldn't pass it back through the humus tanks because it would have joined with the existing site flows and we wouldn't have understood the impacts. We had to put in a temporary solution to mimic what would happen.
Yes.
But ultimately, we imagine it would go back through the humus tank rather than that you would have a lamella stage as well as a humus settlement stage.
Yeah, that's right. So hopefully that answered the question, if I've interpreted it.
Perfect, thank you both. Okay, one more for you, Lisa, from Carl, who would like to know, is there an appetite from the EA to maybe relax consents where a more sustainable solution can be implemented, or would they be willing to offer a temporary relaxation on any pilot schemes?
We certainly have had some great discussions with the EA around, in fact, technologies that we presented today is really they are very willing to step into those conversations and understand how they can best help us to deliver those. But it is tricky. We do have cases where we're taking a catchment-based approach, where maybe if we've got an innovative solution, we're able to have that under a kind of an operating technique agreement, which gives us a 3-year trial essentially to prove that the solution is working before we enter into a full permit. So there are some kind of approaches that we can take to really help us to be more innovative. I know with the natural coagulants, I think Callum's mentioned that we have to work with the EA to prove the performance, and we're doing that through a trial as well, and really kind of trying to collaborate. So these are the right solutions for these sites. We need some time to prove them at scale because we're moving from our pilots into full scale, and the EA have been really supportive with us on that, working with us.
Yeah, probably worth kind of building on what kind of information the EA have asked us to provide as well, because I've mentioned we've done quite a lot of work in kind of getting to a point where we might be able to take them to full scale. So because they are plant derived, we've had to do things like a non-native species assessment. We've had to conduct APEM to do a third-party environmental assessment of the products as well to kind of determine if there's anything in them which would be considered harmful to the environment. So it's not just a case of notifying the EA and starting dosing. There is a lot of additional work that we've had to do in the background, and we've actually been speaking to the EA for around 12 months to kind of get to a point where we can start to move towards full-scale implementation. It's worth bearing that in mind when kind of looking at these new products.
And that will be available to the sector, Leah. So we've done that work with the EA, and that will all be shared as well. So we've kind of done that ourselves on the back of the project, but that can be kind of utilised by other water companies across England and Wales as well.
Perfect. Thank you, Lisa and Callum. So one last one for John from Chris, who would like to know, we've not really spoken about the diminishing supply of virgin pea and how different technologies could create a brand new source of pea for the farming industry. Reactive media being the most obvious if regeneration can be done simply and cheaply. Can you comment on this?
Yes, that will be the key to this technology. If we had a simple regeneration recovery technology, it's something we're hoping to investigate. It was outside the scope of what we were doing under ALT-P here, but we are looking to seek further research funding to look at physical and chemical regeneration methods. If we can look for a way to complete that cycle and recover the pea, reuse it back on land, it's obviously the sensible and addresses all the issues around eutrophication, phosphorus resources, and as I said, maybe a way to avoid phosphogeddon, as they say in the newspapers.
Perfect, thank you, John. I think we have time for just one more question before we wrap up today's session. So Callum, a question for you. The trial was done using natural coagulants. Has a similar test been done with coagulants that are commonly available in the market today, and not necessarily naturally based ones?
So when you say coagulants, I think of sort of ferric sulfate, ferric chloride, aluminium-based products. So we did have a control lane which dosed ferric sulfate, and then the lane that we supplemented with a natural coagulant was also dosing a reduced amount of ferric sulfate. I don't know whether the question might be alluding to sort of polymers like flocculants, which are readily available, fossil fuel derived products. I guess the answer to that is no, we didn't do it because it wasn't in the scope of the project. Our scope was all around, there was a big drive around carbon, so we didn't want to kind of use carbon intensive products. But that is something that we are thinking about in the background. Could we use something like a conventional polymer to do the same job as the natural coagulant in terms of that solids and ion management?
Perfect. Thank you, Callum. I spoke too soon. I think we do have time for one more question. So final question from Oliver, who has asked, what was the control mechanism for the EC method? Did you use the ortho-P measurement to vary power load, flow, or another mechanism?
No, I think I've covered this previously when I talked about control. So it was a fixed dose on the EC lanes. So it was controlled by the current, so that the amps was the set point. We did actually get the suppliers to kind of give us a bit of a cheat sheet. So if you set the amps at 20 amps, what does that correspond to as a milligram per litre dose, so that it meant something to the operators. But essentially it was fixed dose.
Perfect. Thank you, Callum. Okay, cool. So I think that wraps up today's session nicely. Any questions that didn't get answered today during the live session, we will be popping on our platform alongside the written case study and the recording of today's session. So I will be asking the presenters to answer those for you, and we'll share those later. Thank you again to our presenters for the hard work that went into today's presentation. We hope that the audience found it really good and engaging, and has found some valuable knowledge to take back to the organisation with you. As mentioned at the start, we have popped a poll into the chat today just to find out a little bit more about what you thought about today's session. So if everybody could please answer that before they drop off today, they really help us to shape these showcases and make sure they're as valuable for our audience as possible. Thank you again to the audience for taking time out of your day to join us today. As I say, we do hope you found it valuable, and if you do have any more questions for our presenters, I think Callum is happy for you to get in touch with himself. Is that right, Callum? And if not, you're free to get in touch with me, and I can pass on any further questions to the presenters. So yeah, thank you again, everybody, and I hope you have a lovely rest of your day.